Hello everyone, this video is on the topic isomers. What are isomers? Isomers are compounds with same molecular formula but different structural formula. Isomers are classified into two different types. The first one is constitutional isomers and the second one is stereoisomers. And stereoisomers are further divided into cis-trans isomers and the one that is caused because of the presence of asymmetric center. Here are some examples for constitutional isomers. Here we have ethanol and dimethyl ether. Now, when you calculate the total number of carbons, hydrogens, and oxygens, it's going to be exactly the same in both of these compounds. And the only thing that it differs in is the way that the different atoms are connected. So let's count the total number of carbons and hydrogens and oxygens here. So we have C2H6O. So constitutional isomers are compounds which have exactly the same molecular formula and differ in their way that the different atoms are connected. Now let's go on to the next problem. We have propyl chloride, N-propyl chloride, and constitutional isomers. Here are some examples for constitutional isomers. Now we have two examples to begin with. We have ethanol and we have dimethyl ether. When you calculate the total number of carbons, hydrogens, and oxygens in these two compounds, it's going to be one and the same. So in both of these compounds, we have a total of 2 carbons, 6 hydrogens, and 1 oxygen. So these compounds which have exactly the same molecular formula but different structural formula or in the way the different atoms are connected are said to be constitutional isomers. And in the next example, we have 1 propyl chloride and 2 propyl chloride. And you can see that both of them have a total of 3 carbons and then 7 hydrogens, 1 chlorine. And in the next example, we have C3H6O for both of these compounds. And the last one is actually N-pentane, but we know that C5H12 can exist in isomerism with like other branched alkenes as well. And when you calculate the total number of carbons, hydrogens here, it's still going to be C5H12. And these are going to be constitutional isomers. And as you can see, that the molecular formula is going to be one and the same, but their structural formula is different. Okay, now next is the cis and trans isomerism. These are also called as geometrical isomerism, and they result from restricted rotation. And the restricted rotation can be caused by either one of this. One is the presence of a cyclic structure, and the next one is a double bond. Now let's see some examples in both of these categories. Okay, so here are some structures. Here are some examples for cis and trans isomerism that is caused because of the cyclic structure. Okay, now let's try to name this compound, and this is cyclobutane. Okay, we have a bromo substituent and a chloro substituent. So if we want to number this, let's go ahead and number this. 1, 2, 3, 4. So this is going to be 1 bromo, 3 chloro, cyclobutane. But there is a meaning for this bond right here, these bonds right here. These bonds, these solid wedged bonds are actually pointing towards you. And you can see like the same thing is with same kind of bond is actually present towards chloride. So which means you can see that they are pointing in the same direction, which means it should be cis. Okay, so you have to put the cis in front of it. Okay, now let's go ahead and do the next one. So here there is a broken wedge bond. Whenever you have a broken wedge bond, it means that that particular atom is actually pointing away from you. And while Cl is pointing towards you, Br is actually pointing away from you. So which means they are in opposite direction. When you have opposite direction, then you always put a trans in front of it. So this is going to be exactly the same compound, but the only thing that differs in this is the orientation of the different atoms. So here the numbering would be exactly the same, but the only thing that changes here is the configuration, which is going to be trans. So again, 1 bromo, 3 chloro, cyclobutane. Now, let's go on to the next problem. Here we have a cyclohexane, and here again you have two groups that are pointing in the same direction. Okay, they both are actually solid wedges. Okay, and let's start the numbering. Okay, we have only one type of group, so we only have methyl groups on both the sides. So it doesn't matter where we start the numbering from. So I have methyl groups in the 4th position and in the 1st position. So it's going to be 1, 4 dimethyl cyclohexane. That's not the complete name of it. I needed to include the cis of the trans configuration because the two groups are pointing in the same direction. It is going to be cis. And this compound is going to be trans 1, 4 dimethyl cyclohexane. Okay, now let's see whether we are able to write down the structures for these compounds. So we need to draw the structure of cis and trans 1 bromo 4 chloro cyclohexane. So let's draw the structure of cyclohexane first. This is cyclohexane and 1 bromo 4 chloro cyclohexane. So once you have done this, then you have to draw the cis and the trans configuration. For cis, you definitely want both of them to be pointing in the same direction. So you put solid wedges. Or you can also put broken wedges, both the sides. Okay, so these both are actually cis 1 bromo 4 chloro cyclohexane. Okay, now if you want to draw the trans configuration, you have to make sure that you put one bond pointing towards you and the other bond pointing away from you. Okay, so this is going to be trans. Okay, now the next example that we have here is 1-ethyl 3-methyl cyclobutane. So we draw the structure for cyclobutane first, and then we put on the substituents. So we have an ethyl group and a methyl group. So this is 1-ethyl 3-methyl cyclobutane. And if you want to draw the cis and the trans configuration, so this is going to be cis, and if you put one bond facing towards you and the other bond with a broken edge, then it's going to be trans. So this is cis and this is trans. Okay, so the next thing is we're going to talk a little bit about the restricted rotation about the double bond. So we know that the pi bond is caused because of the side-to-side overlap of two parallel p orbitals. And in compounds which has double bonds, there is a possibility you can find, there is a possibility it can exist in cis and trans configuration. Now, how to find whether a compound exists in cis and trans configuration? So here are some rules. Okay, so the first compound, let's see whether it's cis and trans configuration. In general, okay, we know that the geometrical isomerism can exist in compounds where there is restricted rotation across the double bond. When you think of a pi bond is caused because of the side-to-side overlap of two parallel p orbitals, and because of which there is restricted rotation across the double bond. And there are some compounds which can exist in cis and trans configuration because of the restricted rotation across the double bond. Here are examples, and we are also going to go over how to assign the cis and trans configuration for these compounds. The first example is right here. Okay, so how to assign the cis and trans configuration? So you see this double bond right here, and pick one carbon, and analyze the two groups and identify which one is going to weigh heavy. Okay, so between ethyl group and hydrogen, we know that obviously it's going to be ethyl group which is going to be heavy, and you do exactly the same thing on the other side. Okay, so this carbon has a methyl group and a hydrogen, so which one is going to weigh heavy? So obviously it's going to be the methyl group. So because here we have the heavy groups pointing in the same direction, then we call this compound as cis. Okay, now let's analyze the compound on the right. Okay, so you do exactly the same thing. You find the double bond, look into that carbon and analyze the two groups. Okay, here you have an ethyl group and hydrogen. So ethyl group is going to heavy, and methyl group and a hydrogen, this is going to be heavy. So the two heavy groups are on opposite side, and therefore they are said to be trans. Okay, cis and trans can actually be separated. Because they are two different compounds, which is going to have different physical properties. So if you look into the cis and trans configuration, now let's see whether we can identify whether these compounds are cis and trans. Okay, so let's take this compound. Okay, here is a double bond, and you're going to find the two groups, assign which one is going to be heavy. Here, this is going to be heavy, and similarly you do it on the other side. Between the methyl group and hydrogen, it's obviously going to be methyl group which is going to be heavy, and both the heavy groups are on the same side, and therefore this is going to be cis. Let's do for the compound on the right. Here the two groups are on opposite side. The two groups are on opposite side, and therefore this is going to be trans. And here the two groups are on the same side, and therefore this is going to be cis. And here it's actually going to be on the opposite side, and therefore this is going to be trans. Okay, now when we look at the physical properties of this, the boiling point and the dipole moment, you can see the boiling point is actually different for cis and trans. While the cis boils at 3.7 degrees Celsius, the trans boils at 0.9 degrees Celsius. And the dipole moment for this is going to be different as well. So usually for the trans compound, it will be 0. Okay, and again, you can see here, this is a trans compound, and the dipole moment for this is going to be 0 di. Okay, so on the whole, cis and trans are two different compounds which can be easily separated by any way. Like you can separate it by column chromatography or based on the physical properties. Okay, so now let's do some exercises here. Does this molecule exhibit cis and trans isomerism? Okay, so let's figure that out. We have the double bond, yes, and on either side of this double bond you have two groups. You're going to assign the assign which one is going to get high priority. So between chlorine and CH3, which one is going to weigh high? So the answer would be chlorine. Now let's go on to the left side, okay, and assign which one. Here you have two groups that are exactly the same. So in that case, it's not going to exhibit cis or trans configuration. So no cis or trans configuration. This particular compound cannot exist in cis and trans configuration because you cannot assign the priority for the groups. Okay, now let's go on to this again. Here you have the double bond and look into this carbon. Find the two groups and assign priority. So here again you have exactly the same group as substituents. So this compound also does not exist in cis and trans configuration. So for cis and trans configuration to exist, you need to have two different groups on the carbons. So there should be two different groups here and two different groups here where you can assign the priority based on their atomic weights. Okay, let's do some more exercise. Which can exist in cis and trans isomerism? Okay, so let's draw the structure. Let's expand the structure to see the double bonds and all the groups present in it. Okay, so here is my first carbon, or here is the carbon on the left where I have the double bond and on which I have a hydrogen and a CH3. And this carbon has hydrogen and CH2, CH2, CH3. Okay, now let me see whether I can assign the priorities for these groups. Okay, so this is hydrogen and this is a propyl group. Obviously they are different, so I can assign the priority for these groups. So it's going to be the propyl group that's going to weigh heavy. And on the left side I have hydrogen and a methyl group, and here in this case it's going to be the methyl group which is going to get priority. Okay, and the two heavy groups are on the same side, and therefore this is going to be cis. So if you can write cis, definitely we can also have trans configuration, right? So we write the trans configuration switching one of the groups. Okay, so right now or here I'm going to switch these two groups. Okay, so here you can see that the methyl group and the propyl group are in opposite direction, and therefore this is going to be trans. Let's do some more examples. We need to identify whether this compound exists in cis and trans configuration. Okay, again, expand the structure. So you have your C double bond C, and you should have 4 bonds coming out of it. And this carbon has an hydrogen and a methyl group attached to it. So, and again, this carbon has a hydrogen and a methyl group. Okay, so next is to assign priorities between these two groups. We have methyl group, which is going to be heavy, and similarly between hydrogen and CH3. Here again we have exactly the same thing, and this is going to be weighing heavy, and therefore you can see both the groups are on the same side, and therefore this is going to be cis. And you can write the other structure by switching one of the groups. You can switch this or you can switch that. Both of that should result in exactly the same compound. this is going to be trans. Okay, next one, let's identify whether this compound right here exists in cis and trans configurations. Again, you will expand the structure. So I'm focusing on this double bond right here, this double bond right here, and going to expand all the groups so I can see. So this carbon has hydrogen and CH3, and this carbon has two hydrogens, so which means it's going to be like this. Now for this compound right here, you will not be able to identify, or you will not be able to assign the priority. So both are exactly the same groups, right? So in that case, this compound is not going to exist in cis or trans configuration. It's not possible at all. Okay, which one has got zero dipole moment? Okay, what is the dipole moment first? Okay, we are going to identify which one has got zero dipole moment in this problem. Okay, which one of these structures has got zero dipole moment? Earlier in the chapter, we talked about it's only trans compounds which is going to have zero dipole moment. So we needed to actually find the trans compound in here. So let's assign the cis and trans configuration for these compounds. So for this compound right here, you have two Cls on the carbon, which means you cannot assign the priority of this compound, and therefore this is not going to exist in cis and trans configuration. And again, for this one, you again have two hydrogens for which you will not be able to assign the priority, and therefore this also doesn't exist in cis and trans configuration. Now let's go on to this one. Okay, so for this one, you have two groups which are in opposite direction. Okay, and when you assign the priority, this is going to be heavy and this is going to be heavy, and they are in opposite direction, therefore this is going to be trans, and we know that the trans has got zero dipole moment. Okay, and here in this compound you have two groups which are actually pointing in the same direction, and therefore this is cis, but the cis has got dipole moment in one particular direction. Both of the dipole is actually in the same direction, which means it's going to have they are not going to get nullified. But here, while this Cl pulls in this direction, the other Cl is actually going to pull the electrons in the opposite direction, and therefore it's going to have zero dipole moment.